chapter 19. We have this first problem. Find the ratio of speeds of an electron and a negative hydrogen ion. That means one having an extra electron, both being accelerated through the same voltage, assuming non-relativistic final speeds. Now, non-relativistic final speeds means the speeds are low enough for relativistic effects not to take place. So you have the electron, you have the hydrogen ion, and both of them are equally charged. Why? Because the hydrogen ion actually has one extra electron. So their charges are equal and equal to that of an electron. And they are both accelerated through the same voltage. And you're asked to find the ratio of the speeds. How do we work this problem out? We know that 1/2 times mass times velocity squared, which is the kinetic energy, is equal to the charge multiplied by the voltage. So that's the equation that we're going to use for both of them. So that's for the electron. M sub E is the mass of the electron, and then you have the velocity of the electron. And then we have the same equation for the hydrogen ion, where the H shows the hydrogen ion. And the right-hand sides are equal because their charges are equal and their voltages are equal. And so now when you divide one equation by the other, you're going to get on the left-hand side, the halves cancel out. And then on the right side, you get 1 because it's QV divided by QV. And then when you rearrange this, you get VE squared by VH squared is equal to MH by ME. And then make VE by VH the subject. You take the square root, plug in the mass of the hydrogen ion, which is 1.67 times 10 to the negative 27, that's given in the problem, divided by the mass of the electron, that is 9.11 times 10 to the negative 31 kilograms, which will also be given. When you take that ratio, you get 42.8. That means the electron speed is 42.8 times bigger than the speed of the hydrogen ion because its mass is much smaller. So smaller the mass, higher the velocity when accelerated through the same voltage. Second question, and the second question reads, a bare helium nucleus has 2 positive charges and a mass of 6.64 times 10 to the negative 27 kilogram. So that's the helium nucleus. We got to calculate its kinetic energy in joules when it moves at 2% of the speed of light. And then what is this in electron volts? So change the kinetic energy into electron volt. And then what voltage would be needed to obtain this energy? So we have 3 parts to this question. Let's go ahead and do it. And in order to do this, we are asked to calculate the kinetic energy, and kinetic energy is 1/2 times mass times velocity squared. So 0.5, which is 1/2, mass of the helium nucleus is given, 6.64 times 10 to the negative 27. Multiply that with the 2%, with the velocity. Actually, in 2% is 0.02, which is 2 by 100, times the speed of light. Okay, so which is 3 times 10 to the 8. So that whole thing is the velocity of the helium nucleus. And when you square that and calculate, you get 1.20 times 10 to the negative 13 joules. And now we got to change it into electron volts. So I'm taking the actual number, which is 1.195 times 10 to the negative 13. And then we know that 1 electron volt is 1.60 times 10 to the negative 19. So when you do that, you get 7.47 times 10 to the 5 electron volt. And in the C part, what voltage would be needed to obtain this energy? We do just like we did the last problem. We set the kinetic energy to be equal to E or charge times the voltage. Kinetic energy is charge times the voltage. Now that we have the kinetic energy, you just got to divide it by the charge to get the voltage, which comes out to be, when you calculate, because see, that's the charge of the electron, and that comes out to be 3.73 times 10 to the 5 volt. So that's 0.373 million volts required to accelerate it to that speed. Question number 3. What is the average power output of a heart defibrillator that dissipates 400 joules of energy in 10 milliseconds? So we have to find the power. Power is nothing but energy over time. So the energy is given and the time is given. This is such a simple question. So all you got to do is divide the energy given by the time. So here we have power is energy over time or work over time. And the energy is 400 joules. 10 milliseconds is 10 times 10 to the negative 3, which is, you're dividing it by 1,000 because 1,000 milliseconds make 1 second. So that's why you have that there. And you get your answer is 4 times 10 to the 4 watts. And then the question B says, why doesn't the defibrillator produce serious burns? Now, it doesn't produce serious burns because this energy is acting for a very short time. Car has to be given kinetic energy, it has to be given potential energy, and also it has to be moved by applying a force which is given to move it at that constant speed. So there are 3 ways in which work is to be done. The way we do it is, you just put the total energy that's required as the sum of the kinetic energy, the potential energy, and the work done, which is the product of force and the distance moved in 1 hour. Okay, so you have the kinetic energy there, potential energy, and the work done, which is force times the distance moved in 1 hour. And to find the distance moved in 1 hour, you're going to go multiply the velocity with the time. So, and the time needs to be in seconds. So the velocity is 25 meters per second, and the time is 1 hour, which is 3,600 seconds. So when you plug that in, you get 1/2 times mass times velocity squared plus mgh, which is for the potential energy. And then the force is 500 newtons. 500 newton times velocity is 25 meters per second. And the time for which it moves is 3,600 seconds. So when you do all that and calculate, you get it to be quite a big number, because this car is getting kinetic energy, potential energy, and it's also being moved at that constant rate for 1 hour. And all this is coming from the battery that is in the car. So that is 4.67 times 10 to the 7 joules. And okay, but the question really says find the charge. So once you get that total work or total energy required, then you go multiply it with the charge times the voltage, as we have done in the other 2 problems. So the total energy divided by the voltage will now give you the charge required, which comes out to be 3.89 million coulombs. That's how you do that question. Here's question number 5. Find the voltage near a 10 centimeter diameter metal sphere that has 8 coulomb of excess positive charge on it. What is unreasonable about this result, and which assumptions are responsible? So first, find the voltage near this charged metal sphere. So the idea here is that we know that the charges on a metal sphere could be imagined to be all concentrated at its center. So we could now take the formula for voltage due to a point charge and calculate this voltage, because we are assuming that the entire charge on the sphere is now placed at its center as a point charge. And so when we do that, we use the formula for a point charge. Voltage due to a point charge is given by kq by r, where k is that constant, which is 9 times 10 to the 9. And the charge in this case is 8 coulombs divided by the radius. And the radius is 5 centimeter, which you change into meter to get 0.0500. And that gives us 1.44 times 10 to the 12. Okay, what is unreasonable about this result? No sphere can hold such a big voltage. You remember that it's 10 to the power 12 volts. Long before that, the sphere would discharge and lose all of its charge, because the air around it would become conducting. It would be kind of a lightning produced in the room. This is exactly what happens when the voltage on the clouds builds up to such a large value. And why did we get such a result? It's because we assumed that the sphere has a charge of 8 coulombs. And that's a huge amount of charge. And no sphere can hold that amount of a charge, because long before that, like I said, it would discharge. So there is a particular limit to which a sphere or any object can hold a charge. And that's where the idea of capacitors comes in later. Because in a capacitor, we are trying to make it in such a way that it could hold a bigger charge without discharging. Okay? So that's the idea of a capacitor. We'll get there in about maybe like 3 or more problems. Here is the next problem. This is about a living cell, and the voltage across this membrane or across the cell walls is given as 80 millivolt, and the membrane is 9 millimeters thick. And what is the electric field strength? See, electric field strength is simply voltage divided by the distance. So this is like 2 parallel plates with a voltage, and you're trying to find the electric field. So the voltage between the 2 plates A and B is given. That's between the 2 cell walls, the opposite cell walls, as 80 millivolt, which is 80 times 10 to the negative 3. The distance is in nanometers, 9 nanometers, and that is 9 times 10 to the negative 9. And then when you do the calculations, you get 8.89 times 10 to the 6 volt per meter. Look at the unit. It's volt divided by meter. So it's volt per meter. That's how we work with a capacitance. What capacitance is needed to store 3 microcoulomb of charge at a voltage of 120 volt? So the charge is given, the voltage is given, and you're asked to find the charge, the capacitance. Pretty simple, straightforward. To find the capacitance, use the formula Q is equal to C times voltage, and then rearrange to get the capacitance as the ratio of the charge to the voltage. The charge is 3 microcoulomb, which is 3 times 10 to the negative 6 micro is 10 to the negative 6, and then the voltage is 120. So when you divide that, you get the answer as 2.50 times 10 to the negative 8 farad. Farad is the unit of capacitance. So that's about the capacitance of a living cell. Find the capacitance of a parallel plate capacitor having plates of area 5 meter square that are separated by zero point 0.1 millimeter of Teflon. So Teflon is the dielectric. Teflon is the material between the parallel plates. It's the dielectric, or it's the insulator. So the area of the plates is given, and the distance between the plates is given, and Teflon has a dielectric constant which will also be given. So the formula for capacitance of a parallel plate capacitor is K epsilon naught A by D, where K is the dielectric constant of the material Teflon. Epsilon naught is the permittivity of free space, which is 8.85 times 10 to the negative 12. That will be given. Then A is the area of the plates in meter squared, which is 5. And the distance between the plates must be in meter. So we change the 0.1 millimeter into meter by multiplying by 10 to the negative 3, which is equivalent to dividing it by 1,000. And then we get 9.29 times 10 to the negative 7, but that can be written as 0.929 times 10 to the negative 6. I shifted the point here. Okay, so 0.929 is 0.93, and since we have 10 to the negative 6, when you write it as 0.929, you can express it as microfarad. So that's how you work out this problem. There is a combination of capacitors, and you have to find the total capacitance. So when you look at this figure clearly, these two capacitors, 10 microfarad and 2.50 microfarad, are connected in parallel. And the third one, which is the 0.3 microfarad, is connected in series to that combination. So these two are in parallel, while the third one is in series. In a parallel combination, the formula for a parallel combination of capacitors is simply add the two capacitances, and we'll keep it in microfarad. So 10 microfarad plus 2.50 microfarad gives 12.50 microfarad. And so you can replace these two capacitors with that single one, and then that is in series with the third one. And the formula for a combination in series is 1 over the total is equal to 1 by the first one plus 1 by the second one. And I am just using the math there. You may as well put it as 1 by 12.5 plus 1 by 0.3. Okay? Or I have taken the lowest common multiple. I just multiplied those two and put it up there. This is an easy way to remember, and then you flip it. Let me stop it right there. When you flip it, why do you have to flip it? Because it's 1 by CS, and we have to get CS, so you got to flip it. When you flip it, the product goes on top, and the addition comes down below. So this formula will always work for two capacitors connected in series. That is, take the product divided by the sum. The product divided by sum. So that's what I'm doing here. The product of the two divided by the sum of the two. So when you do that, when you write that down and calculate, here I have the sum of the two, and here I have the product. You get the answer as 0.293 microfarad. Remember that in series, the total capacitance is always going to be smaller than the smallest amongst them. And the smallest was 0.3, and you see that the total capacitance became even less than that. In this problem set, here you have a 9-volt battery, a 2 microfarad capacitor, and a 7.4 microfarad capacitor. Find the charge and energy stored if the capacitors are connected to the battery in series, and then you have to do the same for the parallel combination. So you have a battery and 2 capacitors, and at first they are connected in series. All right, in order to do that, work that out, this is a kind of the picture that you have. I'm just changing it from 3 to 2. So here you have 2 capacitors, and you can replace them with the total capacitance. The two are 2 microfarad 7.4, and the total capacitance is in series. It's calculated using the formula. Remember, I told you there is an easier way of doing it. Just take the product divided by the sum, and you could just go 7.40 times 2 divided by 7.40 plus 2. Well, I have taken the longer route, but you can just do it that way, or do it like this in the calculator. Okay, so let me repeat that. You either go take the product by sum, 7.40 times 2 divided by 7.40 plus 2, which will give you the same answer as I get here, which is 1.757 microfarad. So once you get that, to find the charge, use the charge formula, which is the product of the capacitance and the voltage. And so multiply the capacitance value, which is 1.57. Remember, we're using the total capacitance. Why? Because we know that in a series combination, the charge on both the capacitors will be the same. Oh, that's so important. In a series combination of capacitors, the charges on both the capacitors will be the same. So right now we got 14.17 microcoulomb, which will be the charge on both the capacitors. And it does not matter what the values of the capacitances are. Like in this case, you have 2 microfarad and you have 7.40 microfarad, but still they both hold the same charge. And then you got to find the energy, and to find the energy of a capacitor, the formula is 1/2 times c times velocity squared. Or you can use, there are 3 formulas, but you have to use the correct one. In this case, the correct one is going to be the one involving charge and capacitance. Why? Because we already know the charge on each capacitor is the same. We got its value, and we know the value of the capacitance. But if we try to use another formula, we'll have to first find the voltage. Okay, so let's go with the charge squared divided by 2 times the capacitance. That's for the first one. But remember, I'm keeping it in micro. All right, so the charge is in microcoulombs, capacitance is in microfarad. So I'm going to get the answer in microjoules. Why? Because this micro is going to be squared, leaving the unit as microjoules. Now do the same for the second one. For the second one, use the same formula, but do remember how I got the micro there, because there's a square on the micro and there's only micro below. That will leave 1 micro. So that's why it's that's why it's 13.57 microjoules. Now in the second one, we got to find what happens when it's in parallel. And again, there are only 2, but this diagram shows 3, but it serves the purpose. The formula can be applied now, but before that, got to understand, when capacitors are connected in parallel, the voltages are equal. So when capacitors are in series, the charges are equal, but when capacitors are in parallel, the voltages are equal. Now, knowing that, we now know that each capacitor is connected individually to the 9-volt battery, and that helps us figure the charge on each one. Charge is capacitance times the voltage. The voltage is the same on both. Why? Because it's connected in parallel. So that gives us 18 microcoulomb for the first one, and then when you do the same thing using the value of the second capacitance, you get 66.6 microcoulombs. But when we try to calculate the energy here, we have to use 1/2 CV squared. Why? Because now we know the voltage. We know that the voltage across both the capacitors is 9 volt. And we know the capacitance of each one. So when we use this formula, you can get the value of the energy stored in each capacitor. So the first one is 81 microjoules. And when we use the same formula for the second one, it's 1/2 times the value of the second capacitor multiplied by the square of the voltage. So you get the answer to that as, oh, it's just coming up 299.7 microjoules. And now, friends, students, just like this video, post a comment, and if you want to get the new videos as soon as they are produced, go ahead, subscribe, and do not forget to hit the bell on the side so you get that intimation whenever I post a new video. Thank you and good luck.